The next part, we are going to talk about two new tests for positive term series that will help us with convergence and divergence. And those are going to be a direct comparison test and a limit comparison test. So for the first part, we need to look at two series, and we're going to write out the first 5 terms of each series. So if we look at our first term of a sub n, and we are going to substitute in our values, then for the first one, we're going to have 1 over 2 plus the next term is 1 over 4 plus the next 1 over 8 and so on. And then we have our next series, series B, that's going to be 1/3 plus 1/5 plus 1/9 and so on. And so here we can compare now our two series, and we see that A sub n is certainly greater than B sub n. And so notice that too in part 4, then we can go ahead and find that A sub n is a geometric sum or a geometric series, and we can find the sum here. And again, that formula is your first term over 1 minus your ratio. And so we're going to have 1/2 over 1 minus a half. And so that sum is going to be 1. So using that, now we can compare here and say that, well, if I know series B is smaller than series A, and if series A has a sum and converges to 1, then we can say that we know that the series from n equals 1 to infinity of B sub n, that has to be less than 1 because it's smaller than our A series. So that's just some things that we're talking about when we talk about a series being smaller or larger than the other. Okay, so for our next thing that we're going to look at is called the direct comparison test. And so notice that we have a particular order with these. And here the order, notice that A is going to be bigger than 0, so it's positive, but it's smaller than or equal to B. And then here again, B is also going to be greater than 0. And so look at what this is telling us, is that if B sub n, if this series here converges, then A sub n has to also converge. So what we talked about is going to be LC, large converges, small converges. So LCSC. And then down here, if A sub n diverges, then B sub n diverges. So then we call this SD, LD. Just to help us remember, large converges, small converges, LCSC, or SDLD. And so both of those together, we do have to make sure we are talking about positive terms. And again, keep in mind the order that you're looking at these. All right, so let's look at part A and use that direct comparison test. And so for A, you have the series 7 over the cube root of n, and it might be a good idea to go through n equals 1 to infinity of 7 over n raised to the 1/3. Now we know that here, if we're trying to figure out what to compare it to, then over to the side, this right here would be a big indicator because I know that 1 over n to the 1/3, I know that series might either converge or diverge if we talk about the P series. And if we go back and think about that P series, then I know this series here diverges. So if we're talking about or thinking about a divergent series, then we're talking about SD, LD. Small diverges, large diverges. So what we need to make sure we know then is 1 over n to the 1/3. That has to be smaller than 7 over n to the 1/3. And notice that is true for all n values that are, of course, let's look here. Yeah, we can't be here equal to 0. So for all n, and we couldn't have the fraction anywhere between 0 and 1, that definitely would not be true. So here, for all n greater than 1, so we've got everything in place that we need to show. And so we can say that here, let's see, we got that. So we can say that the sum from n equals 1 to infinity of 7 over the cube root of n will diverge by direct comparison test. All right, so let's go ahead and look at the next one. Let's look at part B. And again, a lot of times it's very tough to tell what to compare this to. So I would look at dominating factors. And so to me, I would say, okay, I'm going to compare that really, let's take that off. I'm going to compare that to 2/3 raised to the nth power. Because if I just focus on the main parts, notice I've got that sitting there. Now, of course, these two aren't the same because the denominator has a 1 plus 3 to the n. Now, I know this is geometric. And again, I know that because I would be multiplying by 2/3 each time. And if you're not sure, string out some terms starting with 1 and you would see that. And let's do that. This would be a good practice here. N equals 1 to infinity. Of that, well, if I plug in 1, I get 2/3. Plus, if I plug in 2, I get 4 over 9. Plus 3 is going to be 8 over 27. So we see pretty quickly that we are multiplying by the ratio of 2/3 each time. So this is geometric. And so if this is geometric, then I also know that this converges because my ratio, the absolute value of that ratio, is between 0 and 1. This ratio here is 2/3. Now, I know that converges, so now we're talking about an LCSC. That looks like a 0. So large converges, smaller converges. So I want to compare 2/3 raised to the n. I need to compare that to 2 to the nth over 1 plus 3 to the nth. And we're going to see that this over here is going to be larger than 2 to the nth over 1 plus 3 to the nth. That denominator is growing a lot faster than the other denominator, so we definitely see that to be true. And so now we have larger converges, smaller converges. So now we can again say that here from n equals 1 to infinity, then 2 to the nth over 1 plus 3 to the nth converges by the direct comparison test. Okay, let's look at another example. Okay, so for this next one for part C, again, to look at what might be a good thing to compare to, look at your highest power on top and your highest power on bottom. So if I look at n over n cubed, that's really like looking at 1 over n squared. And so I know that 1 over n squared here, this converges. I know that converges by the p-series. Good to remember that. So now we're in the part where we know this particular series converges, so we need to set up the large converges, small converges. So we have LCSC, And so we need to really compare some terms. And so I'm going to call this sequence here a sub n. That's going to be our 1 over n squared. And then I'm going to call b sub n, just my other, I'm going to call that our n minus 1 over n cubed plus 3, because we do need to look at these terms. So we're going to start at 1, and so our first term would be 1. If I plug in 2, I'm going to get 1/4. If I plug in 3, I'm going to get 1/9, and so on. Now let's plug in on the bottom one. We're going to have 0. If we plug in 1, we're going to have 1 minus 1 over 4, so 0. And then we're going to plug in 2, so I'm going to have 1 over, let's see, 2 cubed 8, so 1 over 11. And then if I plug in 3, that's going to give me 2 over 30. And so we do see that here that 1 over n squared is certainly larger than n minus 1 over n cubed plus 3. And so therefore, by the direct comparison test, then we can say that the sum of n equals 1 to infinity of n minus 1 over n cubed plus 3, we're going to say that definitely converges by the direct comparison test. All right, now let's go ahead and look at part D. And again, it's a good idea to try to figure out what to compare this to. Maybe go through and check out isolating our terms here. And really, the 8 and 2 is not going to make that big of a difference in the grand scheme of things. I'm just going to look at those two. And so n squared over n cubed, that's 1 over n, so that's a good thing to compare to. And we know that 1 over n diverges. All right, so if we have diverges, then we're talking about SD, LD. And that's going to be small diverges, large diverges. So SDLD, then we need to compare, and I'm going to call this sequence a sub n. We're going to call that 1 over n, and then we're going to have b sub n, and I'm going to call that this monstrous sequence here, 8n squared plus 1 over 2n cubed minus 1, just to establish that one series is sequence is larger than the other. So if we plug in for a sub n, we're plugging in 1, starting there, so that's going to be 1, and then the next one, 1/2, then 1/3, and so forth. Now let's look at the next one. So if we go plug in for our next term, then we're going to have, if we plug in 1, we're going to have 8 plus 1, so we're going to have 9 over 2 minus 1, so 2 minus 1, 1, 9. All right, sorry, brain fart. And then we're going to go to the next one, we're going to plug in 2, and so we're going to have 2 squared, so that's going to be 4, 4 times 8, 32, so 33 over, and let's plug in 2 in the bottom. We're going to have 8 times 2, 16, 16 minus 1 is going to be 15. And so I think we can say that 33 over 15 and 9 over 1, those are a lot larger here. We see that B sub n is definitely larger than A sub n. So we do have a small diverges, large diverges. So by the direct comparison test, the sum n equals 1 to infinity of 8n squared plus 1 over 2n cubed minus 1 diverges. Okay, I did skip part of the example in your notes, so just skip over that. Now let's look at the limit comparison test. And the limit comparison test is very useful, and we will use this quite a bit. The first part of this, again, you are making sure that all of your terms are positive. And then whenever you look at the limit of the ratio of one sequence to the other, that limit value, if it is positive and finite, then either both series will converge or the series will diverge, and it just depends on whichever you're comparing that to. Now, this test again is talking about comparing messy algebraic series with p-series. So again, here, as far as determining which ratio, which value, or which series you put in the numerator and which in the denominator really doesn't change things. Okay, so now we're going to look at the limit comparison test, and notice that the dominating power is n cubed. So I will be comparing this. So I'm going to make myself a note if I can get my pen to write. We are going to compare to 1 over n cubed. Now we need to figure out, I know the directions said limit comparison test, but part of me is like, well, I can see this looks like that we're going to have here. I know 1 over n cubed converges. So if we're talking about that, then we know LCSC, large converges, smaller converges. And it's very tempting to say that 1 over n cubed is bigger than 2 over n cubed plus 4. And for a moment I thought, it looks like it might be. So let's go ahead and let's compare these terms, 1 over n cubed and then 2 over n cubed plus 4, just because even though we're starting at 1, if we plug in 1, we have 1 here. And if we plug in 1 down here, we're going to have 2 over, what's that going to be, 5? Well, yeah, 1 over n cubed is larger, definitely. And so let's plug in 2. So that's going to be 1 over 8. If I plug in 2 down here, I'm going to have 2 over 2 cubed, 12 plus 4 is 16. Oh, those look like they're about the same, right? 2 over 16, 1 over 8. Okay. Well, let's keep going just a little bit more. Let's plug in 3. So that's going to be 1/9. If I plug in 3 down here, I'm going to get 2 over, if we plug in 3, so that's going to be 3 cubed, 27. 27 plus 4 is going to be 31. And so let's see, they were equal there. Let's make sure I plugged in a 2, so that's 1 over 8. Plug in a 2 down here. 2 cubed is 8, and 4, oh, there we go. I thought something looked strange. 2 cubed is 8, 8 plus 4 is 12. I'm sorry. Some days I'm a crackhead. But that's 1/6, so we're still smaller. Let's go on up to maybe some larger terms. I don't know. Let's plug in, I don't know, let's say 5. So if I plug in 5, I'm going to have 1 over 125. And down here, I'm going to have 2 over 129. So it's kind of hard to tell which is going to be larger or smaller here. And in fact, I went over and graphed these, and then after some value, maybe after a half or so, maybe 3 halves, that these really start, this series down here becomes larger than this series up here. So we can't tell. And notice how the numbers are really kind of scrunched together. It would be really hard to go through and tell. So we can save ourselves all of that number crunching time and do our limit comparison test. And we see that each sequence here, all those terms are positive. So we really can just go straight to a limit as n approaches infinity. And it doesn't matter which terms you put in the numerator. I'm just going to put 1 over n cubed just because I want to, over 2 over n cubed plus 4. And notice that's going to end up being the limit as n approaches infinity of 1 over n cubed times n cubed plus 4 all over 2. And notice that this is going to be approaching, let's see, over 2. This looks like it ends up being 1/2. And notice that with this, because these are going to end up really as you approach infinity, those n cubes, and that's going to be 2n cubed. So we're left with a half here. And keep in mind with this series test, that limit value had to be between 0 and infinity. In other words, it's positive and is for sure a value here. So we know that this series here will do whatever I compared it to. And I compared it to a convergent series. So instead of having to go through all those terms, I now know that as n equals 1 to infinity of 2 over n cubed plus 4, that is indeed going to converge because what I compared it to does converge. Oh, and I guess we need to say by the limit comparison test. Okay, so for part B, and again, I'm not going to go through all that messy comparing terms. I don't think that's necessary. So looking at this, what we would need to compare it to, here's our dominating power in the numerator. Here's the dominating power in the denominator. And so I'm going to look at n to the 4th over n to the 5th, which is really 1 over n. And so since that's 1 over n, then I know 1 over n diverges by the p-series. And so here, then we're going to go ahead and go straight to our limit comparison because we see that these terms will be positive. And so we're going to have the limit as n approaches infinity of, and I'm just going to put 1 over n. And if you want to go ahead and multiply by that reciprocal, by all means, go ahead and do that. It's just going to save you time. We know multiply or dividing fractions, you need to flip and multiply by the reciprocal. And so for this one, let's see, we're going to end up here, just isolate, look at your dominating powers. So in the bottom, I'm going to have an n to the 5th, and on top I have an n to the 5th. So this ends up being 4, which again, that limit value is between 0 and infinity. So that tells me that our series that we had, n equals 1 to infinity, of n to the 4th plus 5 over 4n to the 5th minus 2n cubed plus 3. We know that is going to diverge, and I know that because I compared it to a divergent series. So this will diverge by the limit comparison test. All right. Okay, now we will talk about your homework. And notice in your homework, this does ask you to use the direct comparison test here to show convergence or divergence. So that's what we're going to do. And so for number 1, we are going to compare this one, and I hope we're getting better at picking out what to compare this to. But this one I would compare to, let's just say 1 over n squared, because I know this converges. And so we can talk about if that's convergent, then we're talking about LCSC, large converges, small converges. We do have positive terms, so this is a positive series. And so we need to determine that 1 over n squared is certainly larger than 1 over 3n squared plus 2. And we see that is true for n going to be greater than or equal to 1. We see that that is true. And so here we know that our series 1 over n squared diverges. And let's go ahead and jazz that up with a 1 to infinity. Or not diverges. Oh my gracious, sorry guys. We know that converges, sorry. Converges, and again, we do need that 1 to infinity. And so we see that here, the sum of n equals 1 to infinity of 1 over 3n squared plus 2 also converges. And we're going to say by, and I'm going to get lazy direct comparison test. Okay, for our next series, I would compare this to the series 3 over 4, all raised to the nth. And again, I know this would be geometric, and I know the ratio here is going to be 3/4. And so with that being the absolute value of r, it's going to be bigger than 0 and less than 1. So then this would converge. And so with our direct comparison test, we can establish that if we're talking about convergence, then we need the large to converge, small converges. And so here we do see 3 to the nth over 4 to the nth plus 5. That is certainly smaller than 3 over 4 to the nth. And so, and if you're not sure about that, you can think of 3/4 to the n, that's 3 to the nth over 4 to the n. And then you see that adding 5 in the denominator does indeed make that series smaller. So we can say by the direct comparison test that here we have our series n equals 1 to infinity, 3 to the n over 4 to the n plus 5 converges. Okay, looking at our next one, we have 1 over n times 3 to the n, and this one's going to look tricky, but again, the dominating power here is that 3 to the n, so we can compare that to 1 over 3 to the n, which is really the same thing as 1 over 3 all raised to the n. And so again, we see that this is geometric. The ratio is 1/3, and so this will converge. And again, we need to look at large converges, small converges. And if we do that, then we need to establish that 1 over 3 to the n is larger than n times 3 to the n, and we see that it is. And so then I know that this is going to converge by the direct comparison test. All right, and so for number 4, now number 4 looks a little tricky. Let's look at it and see. Of course, we're starting here at n equals wood. And we're going to compare this to, I'm just going to round it in, that we're going to compare this to 1 over n plus 1. And that is going to diverge by the integral test. Okay, so if we're talking about diverges, then we need to talk about small diverges, then large diverges. And so here we do see that 1 over n plus 1 is certainly smaller than the natural log of n over n plus 1. And so here we're going to say that our series from n equals 1 of natural log of n over n plus 1 diverges by the direct comparison test. For this next one, it is tempting to do a direct comparison to the series 1 over n to the 1/3, and we know that's going to diverge by the p-series, but this series here, 1 over n to the 1/3, is greater than 1 over 2 to the cube root of n minus 1. And keep in mind here, if this is divergent, then we're talking about smaller diverges, larger diverges. And so we don't have that smaller. We kind of have it the other way around. So we're not going to be able to do that. And instead of trying to pull out all these different tricks, let's just go ahead and use our limit comparison test. And again, we're going to get the results that we need from that. N approaches infinity. And I'm going to put 1 over n to the 1/3 times our reciprocal, so that's going to be 2n to the 1/3 minus 1 over 1. And so notice that that limit does end up being 2, and so that is between 0 and infinity, and so this we know will diverge by the limit comparison test. So let's go ahead and put that all together. Series from 1 to infinity of 1 over 2 cube root of n minus 1 diverges by the limit comparison test. All right, so let's move on to our next problem here. And so notice that with this one, it sure does look like right here, we can compare that to 5 over 2 to the nth, and we know that that diverges. So if we diverge, then we have to show that smaller diverges, then larger diverges. And so while we're looking at that, we need to establish that 5 over 2 all to the nth is certainly smaller than 5 to the nth over 2 to the nth minus 3. And it is, because here we can think of this as 5 over n over 2 to the n. So this denominator here is getting smaller as this denominator is getting larger. So here we have all of that set up. So we're going to say that here n equals 2 to infinity of 5 to the n over 2 to the n minus 3. We see that that will diverge by the direct comparison test. For this next set of homework, we're going to be using the limit comparison test. And again, very similar, but in my opinion, a little bit quicker and easier here. So for this, we would compare to 1 over 3 all raised to the n. And we know that is geometric. Our ratio is 1/3, so this is divergent. Then we can come back down here and just do our limit. So we'll do the limit as n approaches infinity. And let's take what we're comparing it to, which is going to be 1 over 3 to the n. And that is divided by our term here, but I'm going to multiply by the reciprocal, 3 to the n plus 1 over 5. And so as we approach infinity here, notice that we are going to end up with a 1/5 as all of those ends shoot off toward infinity. So here that 1/5 is between 0 and infinity. So by the limit comparison test, we see that n equals 1 to infinity, a 5 over 3 to the n plus 1 does whatever we said it was going to do, converges. Right, and over here to the side, taking these dominating powers, and let's look, we have n to the 1/2 over n to the second. So that's going to be 1 over n to the 1/2 or 3/2. And so we know by the p-series that this is convergent by p-series if we need to write that out. I'm asked, so I'm not sure if we need to. All right, so we do know that converges by the p-series for sure. And so now let's look at our limit as n approaches infinity. And I'm going to compare 1 over n to the 3/2 times, and then we're going to do our reciprocal, n squared plus n plus 3 over n to the 1/2 plus 2. And so let's look at what happens here with those exponents. It looks like we're going to have an n squared on the top, and then on the bottom, if we multiply those two, that's going to end up with 4 over 2, or n squared. So that's going to give me 1. So here, by limit comparison test, we see that we have from n equals 1 to infinity of this series, square root of n plus 2 over n squared plus n plus 3 converges. Right, for our next problem, I would compare this to 1 over n. So we're going to compare here to 1 over n, which is divergent. It's a harmonic series. Okay, and so we're going to look at our limit as n approaches infinity of, and we're going to have 1 over n times 2n cubed plus 4 over 5n squared. And here, notice we're going to have an n cubed over n cubed, and so that's going to be a 2/5. And again, notice that that 2/5 is between 0 and infinity. So this is going to diverge by the limit comparison test. For our next example, I would compare this to, get my pen to write, that's always great. 1 over the square root of n cubed. So that's going to look like 1 over n to, remember it's exponent over root, so to the 3/2. And so this is a convergence by p-series. Okay, and so let's go through and do our limit comparison. So we're going to look at the limit as n approaches infinity, and we're going to have 1 over n to the 3/2 times the square root of n cubed plus 1 over 1. And so if we're looking at what's going to happen with this, notice that again that is getting pretty close to an n to the 3/2 itself. And so this is really going to balance out to be a 1. And so here this is going to converge by the limit comparison test. Okay, for this next problem, it looks like we're probably going to compare to, let me get that, we're going to compare to, let's say 3 over 2 raised to the nth, and again, I'm pulling that from here and here. So if we're comparing that, well, this is geometric, and we know that this is a divergent geometric, and we know it, geometric, T-R-I-C, sorry, because our ratio is 3/2, which is bigger than 1. So let's go ahead and look at our limit as n approaches infinity of, and let's see, we're going to have 3 to the n over 2 to the n times this reciprocal, which is going to be 2 to the n plus 5 over, let's see, flip that over, 2 plus 3 to the n. And looking at this, you can do some multiplying here, and I would see in the top, I'm just going to look at multiplying here and here. So that's really going to be 6 to the n. Because again, you can do that. You're going to have, let me write out y. So you're going to have 3 to the n times 2 to the n, which with our exponent rules, that's the same thing as 3 times 2 raised to the n. So that's where I'm getting 6 to the n. So that's happening in the numerator. And if we look at this all the way out here, that's going to happen as well right there. So we're going to have 6 to the n compared to 6 to the n. So that looks like that's going to end up being 1. So again, that is definitely between 0 and infinity. So by the limit comparison test, we see that this little booger here is going to diverge. So to write that out, again, to the n plus 5 by limit comparison test, blah, 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 diverges. All right, and so for our next problem here, number 12, it looks like we'll probably need to compare that to 1 over. So again, we're going to compare this to 1 over n cubed, and we know this converges by the p-series. That is convergent. And so again, looking at our limit as n approaches infinity of, and we have 1 over n cubed times this reciprocal over 3n squared minus 1. And looking at the highest powers on top, we have 4n to the 5th. On bottom, I have 3n to the 5th. So that's going to be 4/3, and we see that 4/3 is between 0 and infinity. Yay. So therefore, we know that this will converge by the limit comparison test. Right, for each one of these, and I didn't crop the top part of this, but you're given A through F, and you've got all the different types of tests that we've looked at so far, and you're asked to use at least one of these for each problem. So it looks like you could use the limit comparison twice, but I think all the rest of them we could probably figure out. So let's look at number 13, starting off. Here it looks like with this one, this is a pretty big giveaway that you're going to have a geometric. And so for this one, I would say you're going to use the geometric test, and that's B. And this was geometric. And with that geometric, then we see that our ratio, the absolute value of that ratio, has to be between 0 and 1, and it is. So here then we can go through and say, well, our sum, our infinite sum, is your first term over 1 minus the ratio, and our ratio is 1/5. So here our sum is going to be our first term. Well, that first term is going to be 5 over 1 minus our ratio, and we are multiplying by, it looks like it's going to be by negative 1/5 each time. So that's going to be plus a 1/5. And so here we're going to have 5 over, that's going to give us 6/5. And so that's going to give me 25 over 6. Okay, for this one, now this one's a little bit tricky. We've not talked about this since we first started, but this is going to be an nth term test. Now, everything that we've looked at as we've done the limit as n approaches infinity, then the limit of this sequence has to go to 0 or it will diverge. So notice that if we look at this limit as n approaches infinity, we're going to get 1/3. So for our nth term test, we talked about the limit as n approaches infinity of any sequence we had that had to equal 0. In this case, it doesn't, so this diverges. And let me finish this thought here. The limit blah 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 equals 0 for possible, because we don't know that it does for sure for possible convergence. Okay, moving on to our next. Here, 1 over 3 to the n plus 1. This would be a good direct comparison test. That's what I would use here. And again, I would compare that to 1 over 3 to the n. Now that is geometric for sure, and it converges because our ratio is 1/3. And so with our direct comparison test, we do need to make sure if we're talking about convergent, then we need LCSC. And so the large converges, the smaller converges, and we do see that 1 over 3 to the n is definitely bigger than 1 over 3 to the n and then plus 1. And so therefore, by the direct comparison test, the sum of 1 to infinity of 1 over 3 to the n plus 1, that does converge. Okay, for our next problem, they put an n on the outside and inside. Well, this, I wouldn't use the integral test by any means. It's not a p-series because I'm going to have the same thing as n equals 1 to infinity of 4 over n squared plus 4n. I would probably do the limit comparison test just because I can compare that. Let's compare to 1 over n squared, which I know converges by the p-series. All right, so let's see. We're going to say that our limit as n approaches infinity of, and we're going to compare 1 over n squared times, and we're going to do a reciprocal n squared plus 4n all over 4. Yeah, and notice these highest powers here and here. That's dominating everything, so that's really going to go out to 1/4, which is between 0 and infinity. So this is convergent by the limit comparison test. Okay, so for 17, let's see if we can make this into a p-series. So that would be really awesome if we could. Let's see, we've got n equals 1 to infinity of n to the 1/3 over n squared. And we are dividing with like bases, so we subtract exponents. So that's really n equals 1 to infinity of 1 over, and let's see, that's going to be 6 of 5/3. And so for our P series, P is 5/3, and that is definitely greater than 1. So this converges by the P series. All right, let's look at 18. Oh, this one jumps out again. I would do limit comparison test, just because here in my mind thinking about our limit as n approaches infinity, I would compare that to 1 over n squared. And so you're going to multiply by that reciprocal, and that sets up a nice limit. And notice you're going to get 1, and of course that 1 is between 0 and infinity. So this will converge by the limit comparison test. All right, so what if we not used telescoping, and we've not used the integral test? And telescoping right here, notice this subtraction right there. So notice these terms should be bouncing. They're positive, but they should be decreasing in value. So let's look and see what we're going to get. I'm going to plug in a 1, so I'm going to get a half minus a third plus, and now let's plug in 2, so that's going to be a third minus a fourth plus, and let's plug in a 3. So if I plug in 3, I'm going to get a fourth minus a, what are we going to get there? We're going to get a fifth. So this is definitely telescoping. And notice what's happening here. All of these things, and this would actually end up being plus, and you're going to have that parentheses there. So notice how with telescoping, all of that's going to be canceling out. And so you're really left with here 1/2 minus 1 over n plus 2, because again, that's going to be what's really the first thing that's canceled in that parentheses. You notice the pattern going on here. And so with this, then we can look at our limit as n approaches infinity of 1/2 minus 1 over n plus 2. And notice that that limit is going to be 1/2. So here we see that this series converges, and it's going to be by the telescoping series. All right, and so that would leave our integral test. So again, for our integral test, there were 3 main things that had to be true. First, that this was continuous. Everything hinges on continuous. The second thing, you had to be positive. And the third thing, decreasing. And this puppy's doing all of that. So, goodness gracious. And we're going to actually have to do a U sub with this. So let's look. We're going to talk about, here we're going to do the integral from 1 to infinity of n over, or let's change it to x, because we're looking at an integral now, not a sum. So x over n x squared plus 1 all cubed dx. And several things are wrong here. One thing, you've got an improper integral, so we're going to have to make that quote unquote kind of a u substitution. I use b approaches infinity from 1 to b of x over x squared plus 1 all cubed dx. And then if we do this, the derivative of the bottom is almost the top. Notice the derivative of the bottom is 2x. So we need to balance that out. So I'm going to have to put here, if we solved it, you would end up with a 1/2 that gets thrown out front. And so I'm going to have 1/2 times the limit as b approaches infinity of, and we already know the derivative of the bottom there in our u sub, so that's going to be, here if we did that, we're going to have u to the third negative 3, and then when we integrate that, that's going to be negative 1/2, isn't it? U to the negative 2. And so let's go ahead and do that. You've got negative 1/2, and then times, and that u, I'm going to go ahead and go back to 1 over x squared plus 1, and then all of that's going to be raised to the negative 2, or raised to the second. I've already flipped it over, but then I need to evaluate that from 1 to b. A lot of stuff here. Let's move out that negative 1/2. So I have a negative 1/4 times the limit. As b approaches infinity, let's go ahead and evaluate our endpoints. I'm going to plug in b. So I'm going to have 1 over b squared plus 1 all squared minus top endpoint minus bottom endpoint 1 over, geez Louise, plug in 1 squared, so 2 squared 4. And notice that this is going to go off if we let b approach infinity. That mess is going to go off to 0. And so I'm going to have negative 1/4 times negative 1/4, which is going to be 1 over 16, which is positive, finite, so this will converge.